Imagine stepping outside on a clear night and seeing the sky ignite with ribbons of green, red, and purple light, a breathtaking spectacle unlike anything on Earth. It looks like pure magic, but the Aurora Borealis, northern lights, is actually a dramatic space weather event. According to NASA, auroras are colorful dynamic displays caused by an intricate dance of particles and magnetism between the Sun and Earth. In other words, the gorgeous glow overhead is charged particles from the Sun colliding with our atmosphere. It's a natural laser show on a cosmic scale. But as dazzling as it is, auroras have a mysterious and powerful origin. What if we told you the same solar fury that creates the lights could also threaten our technology and even our everyday lives? Stay tuned, because we're about to unravel the secrets behind the northern lights and the colossal geomagnetic storms that drive them. Mid-October 2025 has been buzzing with solar activity. It was reported that multiple CMEs launched from the Sun between October 11–13, 2025 were heading toward Earth. These are not just ordinary sunspots flaring up. They're billions of tons of magnetized solar plasma hurtling outwards. Forecasters at NOAA and the UK Met Office expected these overlapping clouds to strike Earth around October 16–17 and trigger geomagnetic storms. Indeed, NOAA issued a geomagnetic storm watch warning for Oct 16, expecting a moderate G2 storm, followed by a minor G1 storm on the 17th. But why are so many storm fronts hitting us now? And what exactly causes a geomagnetic storm anyway? Let's dig deeper. Auroras occur when energetic particles from the Sun enter Earth's magnetic shield and slam into our atmosphere. NASA explains, when energetic particles from space collide with atoms and molecules in the atmosphere, they can cause the colorful glow that we call auroras. These particles typically come from the solar wind, or giant eruptions called coronal mass ejections, CMEs, huge bubbles of superheated gas and magnetic fields hurled from the Sun's corona. If a CME is aimed at Earth, it can create a geomagnetic storm, a massive disturbance of our planet's magnetic field. Think of Earth's magnetosphere like a protective bubble. A strong CME slams into it like a cosmic hurricane, compressing the field on the sunward side and causing dramatic shifts on the night side. When conditions align just right, often during the Sun's active periods, these charged particles spiral down Earth's magnetic field lines toward the poles. They collide with oxygen and nitrogen in the upper atmosphere, exciting those atoms and causing them to glow. The familiar greens and reds come from oxygen, while blues and purples come from nitrogen. In short, auroras are the fingerprints of solar storms playing out in the sky. NASA poetically calls it an intricate dance of magnetism and particles. But this dance can carry serious implications for our high-tech world. So, what are geomagnetic storms? According to NASA, they are huge planet-wide disturbances caused by major solar eruptions. They're far more intense than routine daily aurora activity called substorms, which are localized and common near the poles. During a geomagnetic storm, the entire geomagnetic system is tossed around. The key ingredient is a strong CME whose embedded magnetic field makes contact with Earth's field. Scientists note that the worst effects on our technology, from power grids to satellites, happen when these two magnetic fields, solar and terrestrial, connect in just the right way. In fact, NASA scientists have emphasized that phenomena like power grid failures, many satellite failures, and the aurora are closely tied to CMEs. In other words, when the Sun fires a superstorm at us, we can get more than pretty lights. We get potential technological havoc. Historic solar storms show us just how extreme these events can be. The most famous is the 1859 Carrington event, the largest geomagnetic storm on record. When British astronomer Richard Carrington observed a monstrous solar flare on the 1st of September 1859, no one knew it would cause an astonishing chain reaction. The following day, Telegraph systems went haywire under the storm's influence, and the sky erupted in auroras all over the world. Witnesses reported the night as bright as day. Polar lights normally seen only near the Arctic suddenly appeared far beyond the poles. In fact, skywatchers saw the northern lights in the tropics, as far south as Cuba and Hawaii. Imagine seeing green curtains of light above tropical palm trees. Some terrified people even thought the midnight brightness was the sun rising or a nuclear flash. Carrington himself realized his observed solar flare was the culprit, establishing for the first time that powerful solar eruptions can trigger global magnetic storms. This set the stage for how we understand auroras today. Another notorious event occurred in March 1989. A CME hit Earth on the 13th of March 1989, unleashing the biggest geomagnetic storm of the space age. Within minutes, Hydro-Quebec's power grid in Canada failed. 9 hours later, millions were left in the dark. People across North America looked up to see amazing auroras glowing far south, over Florida, Texas, and Cuba. Some even feared a nuclear attack as the red and green sky dazzled the horizon. Ironically, the space shuttle launched that day had a mysterious sensor glitch, though NASA never officially blamed the aurora on it. The 1989 storm taught engineers and governments a crucial lesson. Solar storms can literally black out cities and must be taken seriously. Today, power utilities monitor space weather closely. They know that currents induced in the ground during a storm can surge through long power lines and knock out transformers. As one Canadian scientist said, March 1989 became the archetypal disturbance, showing how solar activity can down grids. Fast forward to the 21st century, solar activity ebbs and flows in roughly 11-year cycles. According to space science reports, we are peaking around 2025. This means more sunspots, more flares, and more CMEs. In fact, researchers note that we're in the highest solar activity period of the last few decades. The most recent notable example was the 10th of May 2024 G5 storm. Classified as a G5, the NOAA scale's most severe level, it was the strongest storm in over 20 years. Amazingly, this storm, nicknamed the Gannon Storm, didn't wreck our grids or satellites, thanks to preparations, but it did create auroras dancing at lower latitudes than usual. NASA reported it was the best documented geomagnetic storm in history, giving scientists invaluable data. They gathered information from satellites and ground stations, from the poles down to the equator, improving forecasts for future storms. Why all the attention? Because a severe geomagnetic storm today could have huge consequences. NASA experts warn that a Carrington-scale event in our modern age might not kill anyone directly, but it could cripple critical infrastructure. The UK government even lists adverse space weather among its top natural hazards. Scientists have grimly speculated that if a massive storm hit without warning, it could cause an internet apocalypse and cost $600 billion to $2.6 trillion in damages in just the US alone. In other words, the sun's tantrums have the potential to knock out communications, GPS, and power on a continental scale. NASA puts it bluntly: geomagnetic storms can decimate satellites, overload electrical grids, and expose astronauts to dangerous radiation. That is why space agencies spend billions on solar observatories, like NASA's Parker Solar Probe and ESA's Solar Orbiter, and why meteorologists forecast space weather day and night. But should you be worried right now? For one thing, it's comforting that NOAA and others give us advance notice. They monitor sunspots and use models to predict when CMEs will arrive. In the case of the OCT 2025 storm train, NOAA forecast well ahead that a G2 storm was coming. That means power companies can brace for possible fluctuations, airlines can adjust polar flights, and satellite operators can put spacecraft into safe modes. And remember, even moderate storms, G1, G2 can be fun too. It was explained that G1, G2 storms can cause minor power fluctuations or satellite glitches and can also bring the aurora as far south as New York or Idaho latitudes. Throughout history and into the future, one thing remains certain. The aurora is both a beautiful wonder and a reminder of our star's power. Every time you see those colors shimmering, you are witnessing particles that traveled 100 million miles to meet Earth. As scientists say, the giant CMEs can contain billions of tons of solar material, with an embedded magnetic field that can play havoc with Earth's magnetic field. We may not always know exactly what the sun will do next, but thanks to satellites and research, we're learning to read these solar tantrums. Meanwhile, if you enjoyed this journey through space and want to learn more about cosmic mysteries, please hit like and subscribe. Let us know in the comments, have you ever seen an aurora, and what do you think about our sun's hidden power? What would you do if the lights went out and the northern lights came to your city? Your questions and excitement keep the conversation alive. The auroras are a natural phenomenon that can delight or warn us, and science is our guide to understanding it. Remember, every spectacle in the sky has a story written in physics and history. So next time the night sky suddenly lights up, ask yourself, what is the sun trying to tell us? Stay curious, stay safe, and keep watching the skies. And don't forget to subscribe for more mind-blowing space science.